Okay, let's take a look here. I want to look at surface area of prisms and cylinders. In fact, I think I don't want to do it this way, though. Okay, surface area of prisms and cylinders. Now, let's talk about what it means. We discussed this a little bit ago. Last week, we talked about what it was meant to be a prism, what it meant to be a cylinder, briefly. We didn't go into a lot of detail. Let's maybe spend a little more time on that. This is an example of a prism. Now let's look at the definition, kind of the anatomy of a prism. What does this mean? A prism is a polyhedron. Now what's a polyhedron again? Going back to last week? Yes, sir.
Three-dimensional shape with no curved sides.
Okay, good. Three-dimensional shape, no curved sides, so straight edges. The faces of a polyhedron are all what? Flat, true. What kinds of shapes are they? If I look at the faces of a polyhedron, they are polygons. Exactly, they're polygons. Okay? All right, very good. So, now a prism is a special kind of polyhedron. A prism is a polyhedron with two congruent faces called bases, right? And the bases are parallel to each other. So they're in parallel planes. So the way you imagine this, remember, is whenever I want to orient a prism, I'm going to set the prism down and put one of the bases down on the coffee table. If it doesn't show up that way in the picture, I can always do that in my head. I'm going to take this thing and reorganize it so it's reoriented so the bases are flat, horizontal. This one's already set up properly, isn't it? The base down here is on the coffee table. There's the top base. Okay? The other faces, other than the bases in a prism, are called the lateral faces. Lateral just means side. That's all it means. Lateral means side. So I got the bases on the top and the bottom, and I've got the lateral sides around the middle. Okay? The edges, we could say, these we could call base edges, because they're the edges of the base, right? But the edges around the side of this thing we'd call the lateral edges, the joints between the lateral sides. Does that make sense? Or the lateral faces, I should say, sorry. Okay, make sense? Now this is a special kind of prism we're looking at here. This is what we call a right rectangular prism because of this right angle right here and right there. So what this one is saying is that all of the lateral edges are perpendicular to the bases. Okay, they don't have to be that way. Let's quickly take a look at what one looks like that's not a right prism. There's one that's not. It's squashed over to the side. Okay, that's what we call an oblique prism. Notice the difference. Notice that the lateral edges this time are not at a right angle to the coffee table. They're slanted, right? This thing is sitting on the base. Notice there's a flat triangular base, and then on top of this thing there's another flat triangular base, both of which are horizontal, right? But it's been pushed over to the side, so it's not a right prism. That's a right prism. Okay? Questions on that? Does that make sense? Okay? So there's a right prism. Whoops. There's an oblique prism. Okay? On an oblique prism, we have to do one thing a little differently. On the right prism, we define, what's convenient about this is, the height of the prism, which is just the distance between the two bases. Isn't that the same thing as the length of one of the lateral edges? Everybody getting this? Okay, make sure everybody's clear. So the height is just the same thing as the length of a lateral edge, right? Because that's a right angle. It's lined up vertically. The prism is, correct? Look at this. This is different. Now the height here is something different than the length of one of the lateral edges because it's been squashed over to the side. So we got to define the length of one of the lateral edges differently than the height. When you get one that's been pushed over like this, the height still means the same thing. The height is still the vertical distance between the two bases. Okay, the distance, the bottom base is sitting on the coffee table, flat, top base is above it, off to the side a little bit this time. and the vertical distance between those. So if I drop a tape measure straight down to the coffee table, that's measuring height. The length of the lateral edge now is what we call the slant height, which is going to be bigger. Slant height. Yeah, the slant height is going to be greater than the height, isn't it? Okay? All right. Questions on that? Okay, so far so good. All right. Okay, prisms are classified by the shape of their bases. So notice that if we go back to these last two examples, we called this a rectangular prism. Why? What do you think?
Because all its shapes are rectangle.
Okay. Okay, now that's partly right. The fact that all of the shapes are rectangles might be interesting, but there's only one of them that we care about. When we call this a rectangular prism, the reason it's rectangular is because of one rectangle in particular. Which one? The base, yeah. The bases are rectangles, and therefore it's a rectangular prism. Now, if the bases were squares, the lateral faces could still be rectangles, couldn't they? Right? If that distance were the same as that distance, if this thing were pretty tall, I'm still going to have rectangular faces along the sides of this thing, right? What would we call that, though? Would we call it a rectangular prism? If the base were square, what would we call it? Well, maybe, but it might not be cubical. It might still be stretched up this way, right? What do you think? No. We'd call it a square prism because the base would be square. Okay. See what I'm saying with that? We categorize, we classify the prism based on the shape of the base. So if the base is a rectangle, it's a rectangular prism. If the base is a square, it's a square prism. Now, if the height happens to also match the length of the sides of the square, then that square prism would actually become a cube. But that's only if the height is right. Otherwise, it's just a square prism. How do we feel about that? Give me a 1 to 5 on that one. I want to make sure we get that. 5 meaning I got that 100%, 1 meaning I don't know what you're talking about, 3 being in the middle. Just covertly there, give me I want you to know how we're doing on this. Okay, all right. Okay, good. That's pretty good. We'll come back to that again, too. So then how would I classify this one? What's that one called? Is it a rectangular prism because the sides or a parallelogram prism because of the lateral sides? It's triangular because the base is a triangle. Right? It's oblique because it's pushed over, but it's a triangular prism. So they're classified by the shape of the bases. Okay? Now, if we want to look at the surface area of any polyhedron, we know that's just adding up the areas of all the faces, right? Now, we can do that with prisms. That's fine. We can do that with prisms. We're going to come up with maybe an easier way of doing it, but that works. If I want to add up the surface area of, say, this guy, without knowing any fancy formulas from the next section in our textbook, knowing just what we already know, take a second and see what it would be. Let's do it. See if you can do it in your head. That's a big calculation. See if you can. Okay, how do we do? How would we go about doing this? We'll see if you can see if you got the right answer. I won't make you volunteer. How could I add up this area? What do you think? Okay, which would be what? Okay, so I get 15 there and down there, right? Okay, now what else? Okay, I'm going to get the front and the back. That would be 24 and then 24 on the back side. And then what else? Yeah, left and the right. I'm going to get 40 there and 40 on that side. So when I add those up, it's just 15 plus 15 plus 24 plus 24 plus 40 plus 40. Well, a nice convenient way of doing that would just be 15 times 2 plus 24 times 2 plus 40 times 2, right? And so if we did all that stuff, what are we going to get? Well, let's see. 80 plus 48 plus 30 ends up being 158. Okay? Works. No big deal. That's always going to work, by the way. You can always add up the surface area of any polyhedron, including prisms, by just adding up the areas of all of the sides of the thing, or the faces of the thing, right? Now, it turns out there's another way of doing that. Oh, okay. Let's take an example of a more complicated prism. Let's take this. How would we classify this one, by the way? Oh. Yeah, it'd be a hexagonal prism. Well, too late. It'd be a hexagonal prism because the bases are hexagons. And the bases are the ones, remember, if I took this thing and set it down on the coffee table, I'm looking at that base and the base on that's currently like behind the thing. Now, why is it, seems to me here, actually it doesn't, but tell me why I'd be wrong in suggesting that it's okay the way it is. The base could be that rectangle on the bottom and that rectangle on the top. They seem to be parallel to each other and they're congruent. How come that doesn't work? What do you think, Jack? Say it again. It's not the base. Yeah, exactly. Somebody explain to me why it's not the base. What do you think there?
Because there are two other pairs of sides, just like that one.
Ah, okay. That's not going to work, is it? Because for one thing, look at this. If I were to make, let me try to draw this, and I apologize in advance for my crappy drawing skills, but let's say we tried to make that the base, and then this the base. This question comes up sometimes. It doesn't work because look at this. If those were the bases, I would have to have straight edges connecting them, right? Which I don't have. Right? The edges would come out and it doesn't work, does it? The edges need to be, if we go back and look at these prisms, notice that the lateral edges are all straight lines. Right? So that doesn't work. That doesn't work this way. Okay, when I'm making a prism, I've got to be able to start with some shape and just pull it straight up through space to carve out that shape. So this time I'd be starting with a hexagon flat on the table and just drawing it up vertically to create the straight sides, right? So I've got to set this thing down like so. So the bases are the hexagons, the rectangles are the lateral faces, right? Now watch what happens if I take this thing and let's say I cut along the seams and I unfold it. This is, by the way, what we call in geometry a net. Unfold a shape to see what it looks like when you flatten it out. Isn't that what we get? Can you see that if I just kind of roll those up, that 1, 2, 3, 4, 5, 6 sides, if I rolled those around, I would make a hexagonal tube, and then I would just fold these ends down, and those would be the caps or the bases. Everybody see that? And if I wanted to add up the area of this flat shape, isn't the area of the flat shape going to be the same thing as the surface area of the prism? Right? A lot of times it's easier to work with a flat shape, though, than it is with something that's, three-dimensional looking, right? Bases are, adding up the bases, I have to just add those up, find those areas on my own. Right? I got to know I got to find the areas of those bases. We'll talk about how to do that, by the way. We skipped a section. We skipped chapter 11, and there's one part of chapter 11 that's important that I'm going to go back to and tell you about, and that's how do you calculate the area of a regular hexagon. It's one thing we didn't talk about. There's a formula you need to know. Now, I'll get to that. But what about the lateral faces? How could I add up the area of the lateral faces? If I look at that shape as a whole, what is it? This whole thing down here. If I ignore the bases, what is that? It's a rectangle. The height of the rectangle, isn't that equivalent to the height of the prism? Right? Now, what about the length of the rectangle? Here's the part I want you to see. What's the length of the rectangle equivalent to? If I were to, let's do this in blue. If I were to take this blue line right here, a little off, I got to do that. If I take that blue line, and when I roll this thing up, it's still blue. Where is it going to show up on my hexagonal prism? It's the perimeter, isn't it? It's the distance all the way around. Distance around the base, isn't it? So if I want to find the area, the lateral area, it's just the perimeter of the base times the height of the prism. So I get a formula out of that. That makes things a little bit easier. Okay, I can just say, right here, surface area of a right prism. Now, this isn't going to work if it's pushed over and it's oblique, but we're going to be looking at right prisms. So if we're talking about a right prism, the surface area is just 2 times the base, 1 for the top, 1 for the bottom, plus the lateral area. The area of the sides of this thing is just the perimeter of the base times the height. Okay? So let's take a look at a couple simple examples, and then we're going to, before we get into the really complicated ones, we're going to have to show you that formula. But for now, we don't need it. So what about this guy? If I want to use that formula, that's supposed to be a 10. If I want to use that formula we just came up with to calculate the surface area of this, what kind of prism is that? Rectangular. The base, it looks like the base is a 10 by 5 rectangle. Okay. How's that going to work? What's the area of the base? 50. Okay, so B is 50. What's the perimeter of the base? How do I calculate perimeter of a rectangle? No, the perimeter, distance around the base. What's that going to do? 10 plus 5 plus 10 on the back plus 5 on the left side. So it's just going to be for a rectangle, it's just 2 times 10. I got 2 lengths and 2 widths. 2 times 10 plus 2 times 5. So 30. Okay. And what's the height? What's the distance between the vertical distance between the 2 bases? Which one of those numbers up there is the height? 6. Sure, that's the height, isn't it? So 6. And all I got to do is plug that stuff in. 2 times the base would be 100, right? Plus the perimeter, 30, times the height, 180. So 100 plus 180 ought to give us 280, right? 280. What do you know? Okay. All right. Now, what about this one? Okay, I want to look at this one because it's not oriented right, is it? Is that prism set up properly on the coffee table?
No.
What do I need to do to it so it's sitting on its base? Which part is the base? How could I set that thing up so it's got a base and vertical sides? Yeah, I'm going to have to prop it up so it's sitting on the triangle, aren't I? Right, so the base is the triangle. What's the height then? 5. Okay, good. Yeah, the height, this is, whoops. That's the height. What's the perimeter of the base? Yeah, here's the base, right? So it's just going to be 7 plus 7 plus 7. 21 is the perimeter of the base. The only thing we need to do here, only calculation we need to make is the area of the base, the area of that triangle. Now I'm going to show you a trick. Here's another thing that comes up. I think it comes up in chapter 11. If it doesn't, you should know it anyway. I'll tell you the little trick here. If I want to calculate the area of a triangle, we know that that's 1/2 the base times the height, right? Always. But in the case that we've got an equilateral triangle, so all the sides are the same length, like this. Let's say that they're all congruent and the length is x. Then there's a little shortcut. We can say the area of this triangle, an equilateral triangle, is equal to the square root of 3 over 4, always, times x squared. Okay? Square root of 3 over 4 times the side length squared is a good shortcut when you're calculating the area of an equilateral triangle, a regular triangle. Okay? So if we do that, oops. Don't we just get that? Right? If we plug in, well, the square root of 3 over 4, side length is 7, so 7 squared is 49. Square root of 3 over 4 times 49. They do this kind of, I don't like the way they do it there, but we could just plug in our calculator. Square root of 3 over 4 times 49. That's the area of the base. We got to double that, right? We said that the perimeter of the base is 21 and the height is 5. So there's our calculation. 2 times the area of the base, square root of 3 over 4 times 49 is how we would think of it, plus perimeter of the base times the height. And our calculator would tell us, if we did that, it's roughly 147 if we round it. Okay? Questions? Okay, is that making sense? Sort of, kind of, maybe? All right. What goes with this, then, that's how we deal with prisms. Cylinders, we said, are like prisms. Now, the good news is that the surface area of a cylinder it's same kind of deal. It's the same formula, only for circles instead of polygons. So as you might expect, if I'm dealing with a cylinder, we're gonna be dealing with circular cylinders, where the bases are circles. Okay? So there are my circular bases, like a can of soup, right? There are the bases, or the lids, top lid and the bottom base. And then the lateral area is going to be a tube, just a circular tube. Okay? We say, just like before, that the height of this thing is just the distance between, the vertical distance between the two bases, right? The two caps of the can. We would call, what else we need to know about this? Nothing really. That's a right cylinder, I guess. We need to probably know that because the sides are vertical. If I set this thing on a flat horizontal coffee table, the sides are vertical. I could push it over and do an oblique cylinder also, but we're not really going to deal with those. Okay, if I want to add up the surface area, there's a little trick, just like before. I can take off the two bases, or just circles, right? The area of a circle is just pi r squared, so that's no big deal. How do I calculate the area of the tube? Now imagine cutting this tube and unrolling it. If I unroll it, what shape am I going to get when I push it flat on the table? Rectangle, sure. I'm going to get a rectangle, and if I look at that rectangle, there's my rectangle. What can you tell me about this distance right there? What's that going to be when I unroll this thing? This red, if I color that red, where's that going to show up on my cylinder?
Of the base.
That isn't it. Right? What do we call that? Perimeter, yeah, but for a circle we can give it a special name. What do we call it for a circle? Circumference, which is just the perimeter of a circle, right? So then we know that the length of that rectangle we get is circumference. The height is just the height, right? The height of the cylinder. So the formula that we get then is for the lateral area for the tube is just circumference, which is 2 pi r, right? We know that circumference of a circle is 2 pi r times the height. Okay, so if we want to write this as a formula, we can just do that. The surface area of a right cylinder is just 2 times the base, which is pi r squared, so 2 pi r squared, plus the circumference times the height, which is just 2 pi r times h. That's it. Okay? So we get a nice convenient formula that always works. What if we want to real quickly just calculate the area of a cylinder, just to make sure we have this down? What's the radius of this cylinder? What's the radius of this cylinder? 3. What's the height? 4. That's really all we need, isn't it? So if I want to calculate the area of this, there it is. 2 pi r squared, well that's 2 times pi times 3 squared, right? 3 squared is 9, so that's going to give me 18 pi if I multiply the numbers, right? Now, this begs the question, why am I leaving that funny pi symbol in there? Is that a good idea or a bad idea? Why am I leaving that pi symbol in there? Why don't I round it? What is pi equal to? Okay, I tricked you. Say it again. Yet a lot of other numbers. Pi is equal to that. It's equal to the pi symbol. It's not equal to any decimal. Any decimal is going to be an approximation. Is that what you're going to say?
Yeah, it's a non-terminating.
Right. It's an irrational number. It's non-terminating, non-repeating. And so that's the way to write pi. You write it as the pi symbol if you want to write it correctly, if you want to get an exact answer. Maybe we're going to end up asking for our answer to be rounded to 2 decimals or something like that. That's okay. But then how do we deal with that on our calculator? Do I plug in on my calculator, when I want to do a calculation involving pi, do I plug in 3.1416 or 14159? No. What do I do for pi? Pi button. Yeah. I'm going to do the calculations with the pi button, and then when I hit enter and I get one big answer, then if I'm asked to, I can round that. Okay? That way I won't accumulate any rounding error. So if I'm plugging into this formula then, 2 pi r squared, we said r was 3, so I'm plugging in 3 for r, and we said h was 4, I'm just simplifying. Like we said, 2 times 3 squared is 18, so I get 18 pi for the areas of the bases combined. And then 2 times 3 times 4 is just 24, so 24 pi is the area of the tube, the lateral area. What's 18 pi plus 24 pi? How do I add those up? Yeah, just add up like terms. They're both numbers of pi, aren't they? So 18 pi plus 24 pi is just 42 pi. If I round that to 2 places, I get 131.95, but that's an approximation. Okay? Make sense? All right, now let's see, how are we doing here? Getting there. Okay, last one. Last problem. This is it. What about this guy? Look at this problem. This is a little different. These are probably the harder problems on the assignment. You're going to get some like this, though, on the test, too. Find the height of a cylinder which has a radius of 6.5 centimeters and a surface area of 592.19 square centimeters. What in the world? How are we going to do that? We know the radius. What do you think? Suggestion?
Use the equation to find the surface area equals 59.
Aha.
592.
Okay, good. If I start with, let's start off with the equation for surface area of a cylinder, right cylinder. Surface area equals 2 pi r squared plus 2 pi rh. Now, we'll plug in everything that we know. We're given surface area, right? So we can plug in, for surface area, I can plug in that number. 592.19, it's just a number. Okay. For radius, I can plug in this number. Now that shows up in 2 places. When I plug those in, look what I get. The S becomes 592.19. 2 times pi times 6.5 squared is just going to be a number, right? Over here I'm going to get 2 times pi times 6.5 times, I want you to notice something, times h. How many unknowns are there in that equation now? 1. If there's one unknown in an equation, we can always solve for it by isolating, right? So all we've got to do is just figure out what this is. Well, it turns out if I do this, 6.5 squared times 2 ends up being 84.5. Okay, we'll take their word for it. 2 times 6.5 is 13, right? So I get 592.19 equals 84.5 pi plus 13 pi times h. Now, how am I going to, and this is important, this goes back to some stuff we did at the beginning of the year. This is the algebra stuff we can't lose for next year. We got to strengthen this. How do I get that h by itself? What are the steps I would go through to get the h by itself? First, I would do what? Okay, good. First, I'm going to subtract this term away, right? First, I'm going to reverse the order of operations. So I'm going to add or subtract first. Subtract 84.5, right? Then what? Divide. I'm going to divide by 13 pi. Whatever's being multiplied by h, I'm going to divide by that. So I divide the whole thing through by 13 pi, and I get my answer. H is about 8. Now they did something bad here that I want to caution you against. They did this. They turned this into, this is from some other textbook, and this is a really bad move. You don't want to do that. You don't want to turn that into a decimal first, right? Instead, what we want to do is we want to divide that whole thing by 13 pi in our calculator, and then we'll round. What does that look like on the calculator? Looks like this. Okay, so if I want to put this in the calculator, if I'm trying to isolate, and you can do this, by the way, you could do this right from here into the calculator. If I want to solve for h, I'm going to have on the other side, getting the h by itself, I'm going to have a 592.19, right? So I can either put that in parentheses if I want to, because I'm going to end up dividing 592.19. I'm going to subtract this 84.5 pi to that side. And my pi button is, you can't see it very well. I can't see it very well.
Towards the second button, it's the caret.
Right there, yeah. So second caret, right there. Second, that button gives me pi. Close the parentheses, and then I'll divide that whole thing by 13 pi. Now, if I divide by 13 pi, that's two things. So I got to put them in parentheses. So I'll divide by the quantity 13 pi. Got to put it in parentheses. If I don't, what I'm asking the calculator is, what is that whole thing divided by 13, then multiplied by pi? That's not what I want. I want it divided by 13 pi. And if I hit enter, I get about 7 point, it's about 8, isn't it? Rounded. Okay. The other alternative is, without using parentheses, I could have done this. I'm going to show, at the risk of overkill, I'm going to show this to you. I could have just said 592.19 minus 84.5 pi. Now I could have hit enter, because on my calculator, if I hit enter, it's keeping that to a huge number of decimal places, so it's as if it didn't even round. Okay? Then, now I want to divide that whole thing, so I can say divided by, and it'll take my previous answer divided by the quantity 13 pi, and notice I get the exact same answer. Okay? Make sense? Either of those is fine. Either of those is fine, but what you don't want to do is this. What you don't want to do is get an answer here and then say round that to 326.73, and then, see what I'm saying? You don't round it until the very, very end. Okay? We good with that? Is that enough for one day? All right.